Hello, good morning. My name is Mel Munch, and this presentation is about the world's ultimate self-sustaining modern green home and what it would look like. This slide shows a second prototype from the Planet Earth Home project I started in 1975. What if you could buy a totally self-sustaining homestead that is both power independent and food independent, with all systems included, and have it assembled anywhere on the planet? It would come complete with all power generation equipment, raised bed gardens, open pollinated seeds, food processing and preservation equipment, water tanks, cages, mating sets of small animals, home automation controls, and even a starting menu plan. It would basically be an entire self-reliant mini farm, shrunk to the size of an average home and yard. It would only require some entry-level knowledge of homesteading. This cutting-edge autonomous homestead system would be designed to basically feed and care for a family while providing them a modern 21st century lifestyle. If this sounds something too futuristic, ask yourself a couple of questions. This slide shows and asks the question about what value do you place on all of these earth-changing and extremely important issues to human beings? I've spent over 47 years of my life on this completely self-sufficient home concept. This presentation today is what I would have wanted to know when I first began this journey as a young man in the mid-1970s. This next slide illustrates some differences between the Planet Earth Home project and other similar projects you may have heard of. Most of these alternative lifestyle home options or systems only produce their own electricity, only rely on the power grid, are not a modern lifestyle, are very small, and or rely heavily on critical purchased products. The last items are important, as the Earth homes are intended to be put virtually anywhere in the planet and are specifically designed to be mass produced. Some of you might be asking, why do these homes have to be mass produced? This slide shows the many advantages to a mass-produced mini homestead. First, keep in mind that mass production actually made possible the lifestyles that we enjoy today. I have a broad background in mechanical, industrial, and manufacturing engineering, many hands-on skills, read thousands of books, spent decades on phone calls and the internet, even wrote a few books about this massive research project. And from my background and experience, this project would be extremely challenging for any one person, a couple, a family, or even a small business. So mass production by a larger organization would help to ensure a quality final product, as well as speeding proliferation of Earth homes over the entire planet. Part of the challenge is that for complete self-reliance, all food production for humans, fowl, and small livestock must be accomplished in a very limited space. This next slide shows the many and very important advantages to producing your own food on site. Perhaps the most important advantage is food security and much better overall health. So for total independence and maximum benefits to human beings, both food and power should be included, not to mention the benefit to this planet. Okay, so let's take a look at what this home system would look like, starting with the structure itself. This slide lists the many common sense qualities that an earth-friendly home should have. The structural style lays a very important foundation for all of the other systems and features. The next slide shows the result of incorporating all those qualities into a single structural style. To increase the overall strength and high wind resistance, cross-member braces are left in place, and the frame is also bolted together for added rigidity. The chiller, some commonly called a basement, as a source of cooler air, avoids the power-hungry air conditioning equipment, and the below-grade space can also be used for rainwater and common food storage. So let's get started. This slide is a view showing the orientation of the pattern of columns in relation to the chiller. Construction begins by excavating a north-south long, narrow trench at a right angle to the east-west pattern of upright columns. At the bottom of the north-south trench, several types of polytubing are put down and then covered with a base layer of pea gravel or small pebbles. A radon-proof rubber membrane is laid down over the pea gravel before a base footing assembly of underground rated lumber. To avoid the massive use of concrete, the chiller is constructed using a technique that I refer to as an envelope braced pre-stressed permanent wood foundation. Note here that the production of Portland cement is the source of about 7% of the entire world's carbon dioxide emissions. It's a very dirty industry. This construction style overcomes a major disadvantage to typical post-frame buildings in that they cannot have a typical basement because they need that space to support the columns. Next slide is a view of the semi-completed chiller looking north. The 2x8 wall sections are assembled horizontally and then tilted into place. Floor joists are laid on top of the foundation plate, which is the foundation of the walls, and attached to butt against the upright 2x8 of each wall section to keep the bottoms of the walls from moving inward from the forces of the soil. The middle of each floor joist beam also has added support from below to help support the weight of several water tanks. Structural steel L angles are positioned and attached at the perimeter bottom corners to support the edges of the floor. This allows air movement between the walls and the underfloor space. Finally, underground rated tongue and groove plywood is then attached. Next slide shows the top of the walls attached to the ceiling floor assembly. High-strength steel banding straps are cut and bent into L shapes first before being attached to the top of every chiller wall stud. The walls are then very slightly tilted outward before a series of strong 45-degree braces are securely attached from floor to wall at the intersections over the wall sections. Before the ceiling joist assembly, which will become the floor of the main living area, is secured to the chiller walls, all of the walls are put in tension to resist the inward pressure of the backfilled soil. This is done by cross-winching the top of the chiller walls to the opposite floor and out vice versa. After the walls are held straight up and down under tension, all of the protruding ends of the banding straps are then bent upward and secured to the outside of the ceiling joist assembly. These now Z-shaped steel bands assure the walls can't be pushed inward because the entire ceiling assembly is holding them in place. The next slide shows a completed chiller before a wide door section is installed. This wide door section allows the entry of larger tanks and containers. Underground rated plywood has been attached to the outside of the chiller. The cracks are then filled and sealed and then wrapped with poly sheeting to help seal the chiller more against moisture. A dual purpose for the long chiller sidewalls is that they double as a huge floor truss to support the upright columns supporting the spanning beams. This is especially important for the central two columns that support the main ridge beam over the main living area. The main ridge beam allows a vaulted ceiling to be put over the top of the center of the earth home. The next slide shows a chiller after being backfilled, and some of the laminated columns have been set into the earth. Small concrete discs or pads have been put into each hole before the column is set to resist the settling of the columns, and it's the only concrete used in the entire structure. Before each column is placed on top of the discs, an uplift anchor is attached to the lower end of each column. After the columns are compacted tightly into the soil, the uplift anchors prevent the columns from being pulled from the soil and basically attaches the entire structure securely to the earth. The details of most of the diagonal bracing, cross bracing, sidewall girts, roof purlins, etc., are similar to other post-frame construction methods and will not be covered here, with 5 important exceptions. First, north-south LVLs, laminated veneer lumber or beams, are bolted together directly over the ridge beam. Secondly, the main and hip roofs use a much larger custom LVL hanger. Third, almost all of the frame cross-bracing is kept intact. And fourth, LVLs have been strengthened by adding a top and bottom stud, basically making them into an I-beam. And lastly, all key structural framing components are also bolted together using 1/2-inch bolts, in addition to many high-strength lag screws. The next slide shows a close-up of a typical LVL hanger that's fabricated from 1/4 inch by 3-inch by 4-inch steel angle iron and bent to its final shape, and then put holes in for the bolts. Bolting together key structural components makes the completed interconnected frame extremely strong and ready for the raised floor, roof, and walls to be attached. A little background here before I get into what kind of roof to put on it. This slide shows the widespread use of rainwater around the world. Rainwater collection or harvesting goes back thousands of years and is commonly accomplished by diverting rainfall off the roof into storage containers. Filtered rainwater is naturally softened, pure, and requires much less energy to obtain. The common alternative is aquifer water. Groundwater is simply well water that over 2 billion people worldwide depend on. However, according to NASA satellite data, a full 1/3 of the largest aquifers in the world are considered significantly distressed, and groundwater pumping continues to reduce the available water volume down there. In addition, aquifers can become contaminated by saltwater, biological contaminants, and industrial chemicals such as petroleum or pesticides. To ensure an adequate and dependable freshwater supply, this home system primarily utilizes filtered roof rainwater, while greatly reducing black water and recycling gray water for other uses. Next slide illustrates the many ways that fresh water is conserved in the earth home system. The world needs to minimize freshwater usage, period. Rainwater harvesting has the added benefits of providing excellent quality water, eliminating soft water salt usage, and saving energy. This slide illustrates the many benefits of steel roofing. This is in contrast to most of the traditional roofing materials, including common asphalt shingles that are less suited for rainwater harvesting, not recyclable, or extremely heavy. These corrugated or profiled steel panels with a durable, sunshine-resistant coating has many advantages for use as a roofing material, including the option to resist condensation. This next slide shows an underside of a typical roof section used in the earth home. Just recently available in the US, steel roofing panels can be laminated with a thin layer of polyester felt that basically eliminates the condensation issues with past steel roofing panels. Provided there is enough air circulation, this thin gray polyester layer acts as a sponge, absorbing condensation at night and then drying out during the daytime. Steel panels can also be used for sidewalls of the home or substituted with many other alternatives. This slide shows a list of just some of the alternative building or material styles that have been used to construct homes. Each style has certain appeals, such as environmentally friendly or green, recyclable, do-it-yourself, energy efficient, cost-effective, locally available, et cetera, et cetera. Note that the earth home sidewalls can be constructed with any of these building styles, depending on location, resources, and homeowner choice. This slide shows the western end of the earth home looking south. For better high wind resistance, vertical exterior walls are made as short as possible by sloping the edges or eaves of the roof closer to the ground using hip roof techniques. The resulting steeper downward slope of the east and west hip roof sections makes the whole structure more rounded, so high winds can more easily pass over the structure. This west-facing utility area shown would contain small animal pens, hutches, and fowl nesting area. The opposite east-facing end, the opposite end to the utility end, would function as a garage, workshop, and storage area with 3 separate entrances for ease of use. Both ends of the earth home have a second level mezzanine that can be used for lightweight storage, or more importantly, a huge area to dehydrate fodder foliage for animal food. On both the southwest corner and southeast corner of the earth home, steel roofing panels can be installed slightly twisted in order to gain much more usable headroom and floor space for both utility room and garage. It's twisted kind of like the pagodas, that kind of not two-dimensional, but kind of a three-dimensional twist to it to gain headroom. Not shown here, the larger middle section between the garage and utility area has a high cathedral ceiling containing the central kitchen, living area, 2 to 3 enclosed bedrooms, laundry room, and bathroom, as well as an upper loft with bedroom and half bath. Just at the top of this view shows the western end of what I refer to as a ridge solar vent cupola that spans the entire peak of the earth-home roof. This shows more about the ridge solar vent cupola viewed from the south. Specially formed dark metal vent louvers are attached to each side of and all the way around the solar ridge vent cupola. These louvers are patterned after those used in Canada and Florida to stop wind-driven snow and rain. Besides the special vent louvers, the ridge solar vent cupola has a clear polycarbonate roof and insect screening all around, and has 2 important functions in the earth home. First of all, the ridge vent cupola encourages airflow by both passive solar and wind activity. As the sun heats up the dark louvers, it causes the warmer and less dense air to escape out of the vents. This negative pressure draws air from many areas in and around the earth home, especially from the 2 enclosed greenhouse areas. Since the ridge solar vent cupola is the highest point on the home, even a slight breeze from any direction will also cause a negative pressure that basically sucks hot air from underneath the roof. This cupola also connects to the north-facing roof, utility area, and garage mezzanine to form a kind of envelope roof. This slide is a view from the loft upward through the ridge solar vent cupola space. To conserve electricity, massive daylighting is achieved by putting a long row of ceiling windows into the very peak of the interior ceiling. The polycarbonate panels on top of the cupola protects these overhead windows from hail, rain, and snow. Daylighting is also used strategically in other locations in the home by locating windows high on the walls of greenhouses, utility, and garage areas. This slide shows a typical roof plenum. The hot air supplied ultimately to the ridge solar vent cupola comes from these north and south roof plenums created by the large space between the upper steel roofing and lower ceiling insulation panels. These pre-stressed ceiling panels are constructed kind of like a sandwich. It uses two layers of foam separated by an airspace with high density foam spacers. This polyurethane foam adhesive, when it's put inside of a clamp fixture, it results in extremely strong and lightweight panel that can span longer distance with a high R value. The warmer air moving through these roof plenums also removes any condensation that might be absorbed by the thin felt layer on the underside of the steel roofing panels. The next slide is a top view drawing of the room arrangements. One of the very important features of the earth home is it is a very user-friendly and efficient floor plan. It took years to develop. As shown, the central raised ceiling, southernmost space, is used for living working areas because of the openness, natural lighting, and views over both the north and south decks. The enclosed bedrooms, bath, and utility laundry areas are under the loft area with windows for daylighting in each room. The next slide is an end view drawing from east looking west. This diagram shows how the cooler air gets into both greenhouses, is warmed, rises, and then flows through the roof plenums to the ridge solar vent cupola space. To summarize, cooler air is drawn in from ground level on the mostly shaded north side, under both of the raised floors, up through both greenhouses, through the roof plenum, into the ridge solar vent cupola, and then outside. Not shown, but hot exhaust air is also supplied to the ridge vent solar cupola from both the utility area to the west and garage to the east, resulting in nearly complete whole home passive envelope venting. This solar ridge cupola, the ridge solar vent cupola is therefore constantly venting air and has multiple advantages. This slide just illustrates some of the advantages and purposes of the whole home envelope venting. Note that this natural passive envelope venting process does not require any electricity at all. Only after these natural passive techniques are utilized should powered climate control methods be used. This slide lists the multiple advantages and uses of the chiller space. The chiller is just one of the many features in the Earth Home that has multiple uses. The major advantage of the chiller is to make use of those stable, cooler soil temperatures for space cooling on those hot summer days. When the interior walls of the chiller are installed, it creates a hollow wall space that connects directly with the hollow underfloor space to create a series of U-shaped air passages. The cooler air contained inside the non-porous pressure-treated walls is not humidified like normal porous concrete basements. This slide just is a close-up view of one of the hole vents in the interior wall of the chiller to allow air to go in and down. To take advantage of those cool exterior walls, a series of these hole vents are put high on the inside wall between each upright stud, all along the chiller interior walls on both, that'd be the east and west walls of the chiller. Air enters these hole vents from spaces inside the chiller, travels down inside the wall cavity, and continues under the floor where it mixes with the even cooler underfloor air. This slide is a section view showing this airflow in its entirety. Since cool air is heavier than warm air, the cool air under the floor and inside the walls of the chiller must be encouraged somehow to make its way into the upper room areas during these hot weather events. Moving the dry and cooler air into the living spaces can be most efficiently done by drawing air from the chiller underfloor area. It is now one large interconnected plenum space. In this way, virtually all of the envelope air surrounding the chiller space is available for cooling purposes, regardless of any enclosed areas, equipment, plumbing, or tanks inside the chiller itself. To first remove the warmer air inside the upper living space, a long peak ceiling plenum is installed just above the loft area, also containing many of these small hole vents. Short interconnecting ducts removes warmer ceiling air from each enclosed room on the main level. So I'm drawing warm air not only from the large living space, but each individual enclosed room as well. This enables the removal of hot air from both the ceiling and the loft ceiling at the same time. Very efficient fans suck hot air from the highest point in the home and blow it down into chiller space. This results in slightly pressurizing the chiller space. Cooler air is brought up into the main level space by a series of large diameter, quiet, and efficient computer muffin fans that can more easily suck this cooler air from ducts that connect from the chiller underfloor level space into the main level space. This air circulation system only uses a tiny fraction of the electricity of common home central HVAC fans. This slide shows the wood stovepipe attachments. By attachments, I mean several means to take advantage of the heat in the smoke leaving the wood burning stove. The first attachment over the top of the wood stove is a thermoelectric generator, or TEG assembly, but it's not shown here. This is designed to generate electricity due to the difference between a hot and cold surface, also known as a Peltier effect. The next attachment that you see in the slide is a heat exchanger that uses the smoke heat to preheat the incoming air into the home. Fresh air is brought into the home to create a positive pressure that helps replace the smoke leaving the home via the wood burning stove. The final attachment is high up on the stovepipe and is the stainless steel flue water heating device. It's jacketed so that the water flows between the stovepipe and the outer jacket. That's what heats up the water. By locating this flue heater farther from the stove ensures that it pre-warms the water safely and efficiently using the thermosiphon principle that does not require any electricity. An evacuated tube solar collector also preheats water in the summer months and is stored in the same hot water tank as the flue water heater. A modulating gas instantaneous, also called demand water heater, is the last step to ensure that the home has a virtually unlimited supply of hot water at all times, with using a bare minimum of gaseous fuel. Next slide illustrates many HVAC current and emergent technologies that can be used with this home design. HVAC is heating, ventilating, and air conditioning. The floor layout and basic design of this home is very adaptable to other heating and cooling alternatives, and virtually any of them can be used in the Earth Home system. The next slide shows just one of the photovoltaic arrays, commonly called PV arrays, used in the home. There is one on the south, one on the north, and one above the eave, but they can be placed mostly anywhere. These photovoltaic panels can be ganged in series, attached positive to negative, negative to positive. This raises the voltage, so they can be located farther away from the central battery bank without losing too much power. Higher voltage travels farther in smaller wires without losing electricity. More panels of any voltage can be easily added as desired by using another inexpensive charge controller. For example, solar panels can be mounted just below the eaves on the south side to make use of this unused space. So it's an area that most people, it's just unused in most homes. So we're using it for solar panels. It also is kind of angled, so it helps drip water off. It's common for the wind to blow when it's cloudy and the PV panels are not producing maximum voltage. The next slide shows a view of a lightweight micro wind turbine mounted on an extended aluminum light pole and guide in multiple places to keep it stable. Recently, lighter weight three-phase wind turbines have gained popularity and can utilize much smaller wire size because they're putting out higher voltage in a three-phase configuration. Next slide shows the base of the wind turbine tower assembly. The tilt-down tower assembly is mounted directly on a base of recycled utility poles that are oriented in an X pattern to basically eliminate the need for a concrete mounting slab. Inexpensive duckbill earth anchors are used for the cables and to prevent the end of the poles from lifting or moving. Next slide shows the worm drive cable crankdown mechanism that makes a much easier job of manually pivoting the wind turbine tower to the ground for maintenance or other purposes. More blades on the wind turbine results in a reduced threat from overspeed as well as lower wind speed startup. More blades prevent it from spinning too fast, basically. The next slide shows how the power in the wind is also can be used to create and store pressurized air. This much shorter windmill with many larger blades is commonly used as a pond aeration bubbling system. This low air pressure or bladder style windmill can be used directly to aerate, thereby eliminating any electricity conversion losses. So water can be bubbled through tanks without using electricity and draining your battery bank. This slide shows an overhead light. It's one of the very important functions of electricity. Low wattage, high lumen overhead light fixtures conserves a lot of power and helps to keep the size of the central battery bank to a minimum. These fixtures use LED light strips and only draws 18 watts of power each. So bringing the total electrical lighting of the entire home, garage, utility area, and both mezzanines, every single square foot of the Earth Home to less than 300 watts in total. Moving on from mechanics to food production, this slide shows a food pyramid about how humans have typically produced their foods. World protein requirements are now predominantly met with 5 very inefficient livestock species, and global agribusiness utilizes just 7 major crops, mostly wheat, corn, and rice. This home system must be capable of not only providing food for the family, but food for the small animals and fowl. To achieve this very difficult goal, the middle two layers on this typical food pyramid must be greatly modified. The exact mix of plants and protein sources would depend on the diet choices of the family. This next slide shows the many diet choices that people have chosen in the last couple of decades for predominantly health reasons. All of them includes vegetables in their diet. And all of these diet choices can be adhered to in the very flexible Earth Home design. For example, if a non-meat diet is chosen, the amount of various beans produced would be increased. This slide shows the selection process for high-value plants. Humans have the capability to eat hundreds of thousands of plant species. To maximize efficiency in the home system, plant species must be carefully selected based on their interdependency and other characteristics. The next slide shows the criteria used to select animals and fowl for use in the Earth Home. There are dozens of other animals commonly raised in captivity around the world for human consumption. Even the Bible makes mention of many other food sources than what we now consume. Feed conversion ratio, or commonly called FCR, is a way to rank livestock based on how many units of feed produce 1 unit of edible food. A low number is good. Rather than the typical polluting and inefficient farm animals we use now, it will be necessary to utilize a lower FCR species. These smaller and more efficient species should be rotated by season in order to make efficient use of the available and natural food sources. Incidentally, if you were to treat tofu as a meat, the FCR beats any meat, fish, or fowl. This slide shows the many present and future alternatives to using soil to grow plants. All of these can be easily incorporated into this home system. Polyculture can be defined as a simultaneous use of several kinds of plants and animals together. Polyculture and companion planting are especially useful because of the ability to control weeds, insect pests, and diseases without adding chemicals to the soil. This slide shows a construction method for the outside raised beds from recycled roofing steel and treated lumber. Raised bed gardens are much easier to maintain and harvest, as well as preventing back strain and injuries from constantly bending over. This technique is also beneficial by allowing the soil to heat up earlier in the spring. That will extend the growing season. This slide shows the same raised beds in the east greenhouse when filled with growing medium and plants. To reliably produce the quantity and mix of food necessary, the Earth Home system layout should include these indoor greenhouse areas. Greenhouse food production should favor dark green leafy vegetables such as kale, collard greens, spinach, and beet greens, alternated with legumes such as beans. Other maturing seed plants and fruit such as squash, tubers, and many other self or open pollinated vegetables would be grown just outside, in the ground, in raised beds, or raised bed trellis system. Also included nearby would be specially designed small perennial or rotated animal food plots that require very little care. This slide shows a number of ways that soil can be fed or improved. For maximum independence, the plant growing medium must be replenished with recycled nutrients that are generated on site. Note here that typical farm soil that have been growing our food for many decades has been depleted of many of its important nutrients, including calcium, magnesium, and sulfur, and only replaced by the common trio of NPK or nitrogen, phosphorus, and potassium. Also, human urine actually contains some 80% of unused nutrients that exit the human body and can be aged and treated to produce a high quality ammonia-like nitrogen fertilizer. Next slide shows some of the various ways that foods can be preserved. During the growing season, most food should be eaten fresh or lightly cooked, which is the most nutritious way to eat. Some foods would be stored for later use, depending on the species, climate zone, and growing cycle. Low energy food preservation would be used extensively, such as common storage, like a root cellar, dehydration, just dry it out, and lactofermentation, such as cabbage, sauerkraut, fermented Jerusalem artichokes, and kimchi. Specialized long-term common storage environments would be used for the hardier food items such as squash, Jerusalem artichokes, garlic, onions, and carrots. The very limited freezer space would be reserved for the more perishable foods such as meat and fowl. This home system is compatible with other optional food preservation methods that require more energy and or time depending on the amount of sunshine, power, and equipment available. This slide gives a glimpse into typical Earth Home diet and what people would eat. The default diet, unless other diet choices are made, would be most similar to a Mediterranean style diet. Salads that include dark green leafy vegetables, raw vegetables, and superfood sprouts would be emphasized. Note that a sprouted seed is some 5 times more nutritious than the seed itself. Eating whole foods or raw foods with natural enzymes should be encouraged. This slide gives just some of the amazing health benefits that the Earth Home lifestyle can offer humans. Health benefits cannot be overemphasized, as they're extremely important to the overall well-being of human beings. This next slide shows the many other qualities and options, flexibilities, and attributes that are too numerous to mention, including easy modification to shrink or enlarge the home to suit different circumstances. This last slide illustrates how small that a total self-sufficient home can be. It is said that there are about 28 very good reasons for going green, and there are many arguments why this home system is the ultimate going green home. I think we as a species should develop and offer a cutting-edge 21st century independent lifestyle modern home system that would help to minimize human impact on the planet. This will lead to a lifestyle choice that will help to create a much more sustainable world. Don't you think we owe it to future generations and to planet Earth to at least try? Thanks for listening.